In this video, we'll be going over trigonometric functions of complex variables. And luckily for us, all the groundwork for this video was laid in a previous video about exponential functions. And the reason for that is because cosine of z and sine of z, where z is a complex number, these are defined in terms of the exponential function. So let's just get into the definitions. Cosine of z is defined as 1/2 e to the iz plus e to the minus iz. And sine of z is defined a little bit similarly as 1/2i e to the iz, and now it's minus e to the minus iz. So these are the basic definitions, and you can see they're defined in terms of the exponential function. And if you want to know why this is the definition, then go to the exponential video and then look at how to expand e to the iz in terms of cosines and sines, and then work this all out, and you'll see that this comes back as cosine of z, and when you work out this calculation, it comes back as sine of z. So now we see that the other trigonometric functions are defined similarly to what we have in real numbers. So tangent z is sine of z over cosine of z. Cotangent z is cosine of z over sine of z. We have secant is 1 over cosine, and cosecant is 1 over sine. And of course, these are only valid where the denominators are not 0. Okay, and then something else we should note is something interesting about cosine of z plus 2 pi. So let's work it out and see what happens. So we're going to work it out using this definition that we have right here. So cosine of z plus 2 pi is going to be 1/2 e to the I z plus 2 pi plus e to the minus I z plus 2 pi. And now we're going to expand this out. We're going to get 1/2 e to the iz plus 2 pi I plus e to the minus iz minus 2 pi I. Now this looks a little bit nasty, but we're just going to keep simplifying. So this equals, we'll do it up here, this equals 1/2 e to the iz e to the 2 pi I plus e to the minus iz e to the minus 2 pi I. And the reason I can do that is if you go back to the exponential video, you see that like in real numbers, when we have e to the something plus something, we can just break it up as e to the first thing times e to the second thing. And now we need to focus on these two terms, e to the 2 pi I and e to the minus 2 pi I. So for the first one, we see that from the exponential video, this equals cosine of 2 pi plus I sine of 2 pi. And cosine of 2 pi is 1, and sine of 2 pi is 0. So this I term goes away, and this just equals 1. For the same reason, e to the minus 2 pi also just equals 1. So what's left after all this dust clears? We see that what's left is, and I'll put it up here, what we have left is just 1/2 e to the iz plus e to the minus iz. And where have we seen this before? We see it right here. So that's the interesting thing to note, is that cosine of z plus 2 pi is the same thing, is equal to cosine of z. And if we do the similar calculations for sine, we'll find that sine of z plus 2 pi is also equal to sine of z. And what does that mean? That means that the period of cosine and sine, even for complex numbers, is 2 pi. So that's a good result to keep in mind. Now we'll go on with our definitions. You might have seen my videos about cosh and sinh, or hyperbolic cosine, hyperbolic sine in previous videos, but just a refresher, cosh of z is defined as 1/2 e to the z plus e to the minus z, and sinh of z is defined as 1/2 e to the z minus e to the minus z. Okay? And now the last thing we have to note, I've just written out already, and this is a different form of cosine and sine. So we've seen this form of cosine written as like this, and sine written as this definition. But the thing about these definitions is that while they're nice and compact, you can't really tell the real and imaginary part because there's i's floating around everywhere. So it turns out if we use this definition for cosh and sinh, and together with the definition for cosine and sine, we get this new definition, which does show us the real and imaginary parts. So we find that cosine of z, which equals cosine of x plus iy, where z equals x plus iy, is equal to cosine of x cosh y minus I sine x sinh y. And similarly, sine of z is equal to sine of x cosh y plus I cosine x sinh y. So these are important because they show you clearly what's the real part and what's the imaginary part of cosine and sine. So these are all basically definitions that you should keep in the back of your mind during complex analysis that will be useful in solving problems like complex integrals involving trigonometric functions.